Let's next talk about area. Now, if you take a piece of paper and you lay it flat on your desk, it's very easy to calculate the area of that piece of paper. Length times width. Let's grab this edge and just use that one edge to represent the entire sheet of paper. I'll draw that down here. And then what I want you to do is I want you to pick up one edge of that piece of paper and lift it up. So here is the sheet of paper, and then lift it up. All right. So this part here is this edge, and this point here would be this edge. So here's the sheet of paper lying flat, and then lifting this edge up, you have the sheet of paper. So you need to imagine that the sheet of paper is actually a rigid board. When you do that, you can look down below and you can see that the shadow cast by the sheet of paper is going to be shorter than the sheet of paper lying on the desk. Do that one more time. Take the sheet of paper, lying flat, and then lift it up. And then the amount of shadow that it casts is going to be much shorter than the sheet of paper lying flat. Okay. And the idea is that these projections, the highlighted pieces, those can be used as the parameter domain. And then these lifted sheets of paper can be the surfaces that we consider, the parametric surfaces. And obviously it's the same sheet of paper, it'll have the same area. However, when we look at the sheet of paper versus its projection, its parameter domain, the parameter domain has a smaller area than the actual sheet of paper. Okay, let's try and make more sense of that. We have these pictures over here. And they are a pair of pictures, so that we have this picture here, and that's the UV axis. And as such, that is the parameter domain D. And then on the other side, we have the X, Y, Z axes. And then sketched over there is a surface. All right, and then we have this picture, which is our domain. Take a point in that domain as an input to our position vector, rvec, and get an output point. So that all of these points mapped over from this plane, the UV plane, under the vector valued function, the position vector, produce the surface, which is a two-dimensional object, and it sits inside of 3 space. All these points get mapped under R into all these points. Points in 2 dimensions get mapped into 3 dimensions. All right. What else can we write down? Let's take that point there. That point has coordinates U and V, and some U sub I and some V sub J. And we're taking that as input to our position vector. And that for that particular ui, vj, we're getting a point P. And then keeping track of the I and the j, we're getting P sub ij. Alrighty. Next, let's read this little caption down here. We see that if we don't just consider points, but rather a line, in particular a grid line, let's look at this guy here. If I highlight that, that's supposed to be a horizontal line. And for that horizontal line, there is a v coordinate, which is held constant. So v is held constant, but then we change u's. And that is a grid line. But each of those points is occurring in the domain. And so it gets mapped over by the position vector. So if we concentrate on this one point, we know that it goes here. And for simplicity, if we concentrate on a point to its left, let's assume that the point on S is this point over here. So let's draw that in with some color. So let's take that grid line. It says that the grid line turns into a grid curve. So let's draw that on the other side, something like that. And then do one more. Let's take this grid line and turn that into this grid curve. Very good. Now let's look down here. And the book uses the notation of T-vec. And T, they use T for tangent. And I think it's a little bit confusing. I would just use R-vec sub V, the partial of R with respect to V. The book, when you read through it, is going to use T-vec rather than R-vec partial V. They'll use T-vec partial V as R-vec partial V. So let's write that down. So T, turn it into a vector. T for tangent. And if we follow, let's go back to this grid line where the V is held constant and we're changing U's. So if we follow inputs along the grid line, the horizontal grid line, then on the image side, we'd be following points along this grid curve. And then at that particular point, if we were to evaluate the partial of R, the position vec, with changes in U, we would come up with the tangent vector to this grid curve. And so they call that T sub U, which is R vec sub U, partial of R vec with respect to U. Likewise, T vec sub V is actually R vec sub V. All right, nice. And again, these are the tangent vectors. Let's look at the next page. And the next page is just the exact same thing. Domain, U, and V, the plane. And then over here, a surface, which is the image of that parameter domain. And they've sketched in the grid curves corresponding with grid lines. But they've also added in the tangent vectors to the grid curves. Now, we know that our parameterization is going to yield a smooth curve. That's going to be the assumption throughout the chapter, otherwise it doesn't make sense. And recall that smooth meant that the cross product of the two partial vectors is not zero, meaning that we have an nvec, set nvec equal to the cross product of those two partials, or the two tangent vectors, which means that we have a tangent plane at the point. Okay, so what did we want to do with this? Well, this is called a surface integral. Earlier, I asked you to consider a sheet of paper, lift it up, and then project it down, and that the domain has a smaller area than the surface. So, relating that to our discussion here of these pictures, we can look at patches in our domain, which we can easily calculate the area of. Just take delta U times delta V. Straightforward area calculation. But then what about the corresponding area on the surface? Well, luckily, since we have a tangent plane, that tangent plane is going to do a nice job of approximating the surface locally. Just think how you have knowledge that the Earth is a sphere, but if you were to stand in the desert, it looks very much like a plane. So locally, it's flat. And if we use that the plane is going to be given by this vector and this vector, then this small patch over here in the domain would get mapped to a small patch over here, which will have area very close to the area of the parallelogram formed by these two vectors, scalar multiplied by delta U and delta V. Let's write that down. So delta S sub ij. S is for the surface. Take a small patch of the surface. Will be approximated by the size of the parallelogram in the tangent plane. And that area of the parallelogram is found by taking the magnitude of the cross product. And then the direction that we want to look is in the tangent direction of the grid curve, where u's change, and in the tangent direction of the grid curve, where v's change. And then we need to relate that back to a change in u's, so that's going to be a delta u, and a change in v's, so delta v. And then doing this out, we can see that these guys are just scalar quantities, so that they can pull out delta u, delta v. And then we're just left with taking the norm of the two tangent vectors. And then this is calculus, so you take a limit, and then over here you're going to get that the delta S will become the differential of surface area, that's a capital S. And over here this will become the area differential in the plane. And then in what plane? So this is my notation, not the book's, U sub V. Convenient to indicate that. And then the guy in front will just remain the same. Very good. So that's collected in the next page as our definition of surface area. Let's write that down, surface area. And that's the surface area of what? That's the surface area of a surface, S. So here we're setting up a surface integral, since we're taking the surface as the domain of integration. The surface is a two-dimensional object, so it necessitates a double integral. And then the book doesn't write it out, but we should understand that we're integrating with integrand 1 against the surface area differential d capital S ds. So SA for surface area, just the notation for the quantity. And then here is a surface integral, a formal quantity with integrand 1. So we're just taking surface area differential. And then to actually compute that out, we can look at the domain D, the parameter domain. And so that would be given in some U's and V's, where we take the area differential in that UV plane, so that's just regular length times width. And then the amount that we scale it either up or down is the size of the cross product of the tangent vector in the U direction with the tangent vector in the V direction. Very good. Nice. Okay, let's do an example. And we'll do an example with this cone over here. And we'll do an example where we actually calculate the surface area. That means that we'll rely on this formula here, which they call 618. Okay, so the first thing that we're going to want to do is come up with this parameterization. So let's take a look at the picture. Let's draw a cone. So let's start with drawing a circle. And then pull that down, and then we have a cone. So in the description, they tell us that the height is h and the radius is r. So let's add in an axis of symmetry so that we can reference a radius r and a height h. So what they do is they introduce a placeholder, an alpha, and they ask you to consider this angle here as alpha. So then you can see that opposite the angle alpha is r, and adjacent the angle alpha is h. Therefore, if you do tangent of alpha, you'll get r over h. As you read this example, the book has a typo. Okay, so what are we doing with that? Well, tan of alpha equals r over h is just going to be shorthand noted as k. So they define that as k. Okay, so we're trying to come up with a parameterization, and all that we've done so far is say that there's going to be an angle here. Pick your r value, pick your h value, then that's going to set alpha. And then if that does, then it's going to be convenient to call that tan alpha, call it k, just a shorthand. Remember when we started drawing this picture, I suggested starting with the circle, and that means that at any height that you pick, here pick a height of h, height less than h, and then take a cross section with a horizontal plane, and you're going to get a circle. And then circles are familiar to us, so let's take some arbitrary height here. And at that height, let's look out from the axis of symmetry until we get to the actual cone. And then draw in the cross section, the circle. And then let's call that height V. Let's call that V. Let's say that that height there is at height V. Then what we do not know is the radius of that circle. Let's call that R, the radius corresponding with height V, R sub V. It's not a partial, it's just a notation. Well, the nice thing is that the alpha is going to be the same, so that the ratio of R sub V over V will equal tan of alpha, or in other words, K. So K is equally tan of alpha, but tan of alpha is also the same thing as R sub V over V. R sub V over V. And then in my setup, I've chosen the value for V. K is a known quantity, so the unknown is R sub V. So solve for R sub V and get K times V. So what does that tell us? This R stands for radius. It's the radius of this cross section occurring at any height V. And the heights that we're interested in are from 0 up to H. So that circle, the purple circle that I've drawn, can be described as kV cosine U, comma, kV sine of U, where U is playing the role of theta, so take U's between 0 to 2 pi. Let's write that out. So they use SVEC in this example. U's and V's at any height V, the cross section will be a circle of radius RV, and then RV is written out as K sub V, K times V, and then for X do the conventional cosine, and for Y do the conventional sine. All right. So here's a circle of radius kV, and then that's occurring at height V. We're letting U play the role of theta, so place a restriction on U from 0 to 2 pi, and we're letting V be the height, and we want V to be taken from 0 up to H. 0 less than V less than H. All right. So that produces the parameterization of the cone in parameters U and V. And in this example, what we're doing is we're finding the surface area of the cone. The cone is a surface, and we want to do calculus to find its area. So we want to compute a surface integral. We want to compute this surface integral. So here's the formal quantity, and what we have done is we have found a parameterization introducing a U and V, specifying a domain. Here's the domain, a nice rectangle, 0 to 2 pi and 0 to H. So that meant that we needed to find a parameterization, and then having the parameterization, we can now simply plug in to the surface area formula, and that means computing each partial, taking the cross product of those partials, taking the norm of that, and then plugging into the formula. Okay. So the partial with respect to U, here's our position vector. v is not u is u, derivative of cosine is negative sine, derivative of sine is cosine. The partial of v with respect to u is 0. And then you can confirm the same thing for the partial of position vector with respect to v gives you this guy, and continue looking at the calculations. Pretty straightforward. Here's that formula. Here's the domain, 0 to h's, those are on v's, 0 to 2 pi, those are on u's, k is a constant. This integrand is the magnitude of the normal vector given by the cross product of the two tangent vectors, which is computed up here. K is a constant, so they're taking the k and the radical term, they're bringing that all the way to the front. You're then just left with v, but the first integral that you want to evaluate is with respect to u, hence you pick up a 2 pi, and so forth. Very good. And I've copied over from the book one other example. The next one, this is worth your time to go through and read through it and verify the computations. Not hard at all, but there are a lot of pieces involved, and so it's worth doing those mental gymnastics for good practice. Very good.